So, hello everybody. Let us now continue our discussion. In the last lecture, we were discussing about the kinetic template effect and the thermodynamic template effect, which is very important in forming rings, cyclic rings of a particular size. And this is preferred because there is always a competition of intermolecular reaction and the formation of the acyclic chain. So, this using the concept of high dilution principle, we are able to now engage the starting materials in a manner that in the presence of a certain cation which serves as a template brings the reactant species into the preferred orientation so that the reaction can take place and then form the cyclic ring. So, and we also looked at the thermodynamic template effect and some of the most important examples pertaining to template effect. Now, we are going to go to the next class of molecules where we are going to look at neutral molecules which have an intramolecular cavity. That means there is a open space which is present when the molecule is formed, and this void or the space which is present exists whether the compound is in solution or it is in the solid state. So, this intracavity persists when the molecule exists in solution or in the solid state. And we have already discussed this. This refers to the formation of cavitates and clatrates depending on whether you have got an intrinsic cavity or an extrinsic cavity. And this kind of host gas complexation molecules complexation now involves organic molecules which can be either polar, non-polar, or a combination of polar and non-polar substituents. And in this regard, we are going to look at two important class of molecules. We will first look at Calixarenes, and then we will look at cyclodextrins. And both these class of molecules are very important because they have a combination of polar and non-polar substituents present on it. And essentially these molecules are also referred to as molecular containers with an enforced concave surface. So, they look like a molecular container, a tub like arrangement, a bucket like arrangement. That is the shape these particular molecules adopt in the solution or in the solid state, and then you can now have guest molecules which can come and interact with the different polar portions as well as non-polar portions of this molecular container, or these cyclic host which have got non-polar content as well as polar content. And there are some general properties which are associated with host gas complexation, because now we have got a neutral organic molecule which is going to interact with a neutral guest in the presence of solvent molecules which are also organic solvents. which can be either benzene, or they can be methanol, or they can be chloroform, and so on and so forth. So essentially the origin of the interactions which are going to dictate these kind of host gas recognition, unlike hydrogen bonds or cation pi interactions or anion pi interactions, are essentially going to involve primary dipole-dipole interactions, where the host molecule and the guest molecule has got a dipole moment, and more is going to be the magnitude of the dipole moment, more is going to be the stabilization energy, because of the interaction of the host and the guest molecules with each other. And the solvent molecules here also play a very important role, and we have already looked at the hydrophobic effect, where you have got a host molecule, it is solvated by the water molecules. Now the guest comes and sits, these high energy water molecules are released into the bulk, so enthalpically it is favored, and also entropically it is favored, because now the initially ordered array of water molecules is now released into the bulk, and therefore the overall entropy change is positive. And therefore from a thermodynamic consideration, the hydrophobic effects primarily drive host gas complexation behavior in molecules which are neutral and having associated with an intracavity. And in most of the cases it will be seen that it is the hydrophobic portion of the host that interacts with the hydrophobic portion of the guest. So they are primarily hydrophobic interactions or lipophilic interactions that drives host guest behavior. So overall the driving force is not very strong, unlike hydrogen bonds or cation interactions, cation-pi interactions, because here we have got the hydrophobic portions which interact with each other. Primarily these are of a dispersive nature, and it will be more appropriate if we can modify or introduce more polar substituents, or we can introduce some anionic feature either on the guest molecule or on the host molecule. In that case, that can drive the process of molecular recognition to a greater extent. And the first molecule we will be referring now in this series is the calixarene, and let us look at the fact how the calixarene molecule looks like. So the calixarene molecule has been I will draw the calixarene molecule for you. And we have got tertiary butyl group here, tertiary butyl group here, TBU group here, and 2Bu group here. And in the interior we have got a hydroxyl group. So this is the representation of a para tertiary butyl calix 4 arene, calix 4 arene, and this compound is prepared by the reaction of synthesis of this calixarene is done by the reaction of alcohol in the presence of formaldehyde and an acidic source, which will lead to the formation of this particular para tertiary butyl calix 4 arene. And in this case the reaction proceeds via the activation of the formaldehyde molecule, and this is followed by the reaction of the alcohol moiety containing the TBU group to form the monomer and then this further again gets protonated, the water molecule goes away, the carbocation is generated, and the carbocation this further undergoes reaction with the nucleophilic center. So, this further undergoes reaction now with the and in this case we now get the next we now get this particular reaction which now gives you the dimer. So, in this case the reaction proceeds and we are able to now finally have the ring closure, and that will give me the calixarenes. Now, this calixarenes which is formed now is having now the tertiary butyl group which is present here. These are the non-polar parts, and the polar hydroxyl groups are present here, and these form a hydrogen bonded array. So, this is the lower rim, this is the upper rim which is hydrophobic, this is hydrophilic because it has got the water molecules, are the hydroxyl groups present, and now this particular site can interact with polar solvents, or it can interact with cations, okay, and this can interact with non-polar, this is non-polar in nature. So, it can interact with the guests which are having non-polar nature, as well as the gas can further interact with the tertiary butyl groups as well. And this is the cavity which is present, the intracavity. In this intracavity we can now include different kind of guest. For example, we can include toluene. It has been observed that now if you take toluene, it has been observed that toluene now interacts with this hydrophobic surface. It now interacts with this hydrophobic surface via the CH-pi hydrogen bonds, and we know that the tertiary butyl groups are present. So, these are electron rich surfaces. So, the CH is the donor and the pi is the acceptor, and we have this CH-pi hydrogen bonds which lead to the inclusion complex of toluene with the calixarene. The next thing which we must realize with respect to calixarene is that this particular molecule is conformationally quite flexible. Okay, it is conformationally quite flexible and it exists in different conformers. Let us look at the different conformers in which this particular calixarenes exists. So, this particular conformation is called the cone conformation. It is called a cone conformation because in this particular conformation all the polar groups are on one side and the non-polar groups are on the other side. So, we can represent it as So all the polar oxygens are on one side and the non-polar R groups are on the other side, and this exists in equilibrium with the partial cone conformation. This is the partial cone conformation where one of the R groups flips over to the other side, and then we have got the other two conformations as well, which are referred to as we call this the 1,2 alternate, and this is in equilibrium with the one, 3 alternate. So these are the 4 different conformations in which my Calixarenes can exist. We have the partial cone conformation, we have the 1,2 alternate, and we have the 1,3 alternate conformation as well. And the cone conformation is a very stable conformation because we have got this OH hydrogen bonds which stabilize it. However, when this OH hydrogen bond, the OH group is replaced by the OR group, then the hydrogen bonds are absent. The hydrogen bonds are absent. So it was also very important to see that now if you add different kinds of cations of different size, what will be the effect on the complexation behavior. So if you have added for example lithium ion or sodium ion, these are oxophilic because they love the oxygen atoms. So the lithium ions and sodium ions coordinate with the oxygen atoms here. They can also coordinate with the oxygen atoms in the partial cone, because in the partial cone one of the oxygen atoms is above but the 3 oxygen atoms are still below, so they can still have a coordination. So it is the partial cone and the cone conformation which is stabilized when you have these oxophilic species like lithium and sodium. However, when you have got a larger size species, then there is a change in the conformation. When you have larger size species like for example the sodium ion or the potassium, the silver cation and the potassium cation, then we get the 1,3 alternate conformer and or the partial cone conformer. We get the 1,3 alternate conformer or the partial cone conformer when we have the larger size silver ion and the potassium ion, and what has been observed is that these are stabilized by cation-pai interactions. These are stabilized by cation-pai interactions because now the silver ion is able to approach in the interior cavity, it is able to approach the walls of this bucket shaped molecule, the molecular container, and interact and form silver the cation-pai interactions, or as well as potassium, which is the cation-pai interactions. Now there is some important data to support the existence of these conformations. So for example, in CdCl3 and deuterated acetonitrile in 10:1 volume by volume ratio in this solution at minus 50 degrees centigrade, it has been observed that the calixarene exists in 70:30 ratio, in 70:30 ratio. So, we can now consider, for example, in general we can now consider R Y. So, R is equal to hydrogen, Y is equal to methyl. R is equal to hydrogen, Y is equal to methyl, R is equal to tertiary butyl, Y is equal to methyl, R is equal to hydrogen, Y is equal to N-propyl. So, we can consider 1, 2 and 3 examples, and we will look at some important data related to the existence of conformations of these calixarenes 1, 2 and 3. So, when you have the CdCl3 CD3CN solution, then what has been observed, the calixarene 1, that is when you have the OH group. So, it is actually the more polar compound. It exists in the 17:30 ratio as partial cone and cone isomer. Okay. So, the partial cone is to cone isomers, it exists in these two particular conformation in this ratio. And we also know that if the solvent is highly polar, then the population of the cone conformer is the highest. So, more is the solvent polarity, more is going to be the population of the cone conformer. Why? Because all the oxygen atoms are on one side and the non-polar portion is on the other side. So, that makes it much more polar, having a higher dipole moment. However, the partial cone conformers, the partial cone can exist in non-polar solution. And also we see that the polar conformation, that is the cone conformer, is also highly pre-organized for binding. Because all the oxygen atoms are in the lower rim and they are more oriented towards interacting with the cationic species. Whereas if the conformation changes to the partial cone, then it is not as much pre-organized for binding like the cone conformer. So, in that case what happens is that now if you now consider the compound 2, in what has been observed in the case of compound 2, when Y is equal to methyl, if you treat it with Ag plus and K plus, then it is the partial cone or the 1,3 alternate conformer. If you treat it with sodium or lithium, then it is the cone or the partial cone, and if you treat it with methyl ammonium compound, then it is exists in the cone conformation. In the cone conformation, what has been observed is that the NH3 plus group. So, now we have got this cone conformation. So, the NH3 plus, which is actually the guest molecule, can now enter inside the cavity which is created by the calixarene and get stabilized by NH-pi hydrogen bonds. Again, this is preferred because you still have the cation dipole interactions. Overall, this is the cationic species which interacts with the calixarene moiety and gets stabilized by NH-pi hydrogen bonds. So, the guest is able to form strong NH-pi hydrogen bonds, and as I already mentioned, if one of the molecules, that is for example the guest molecule, is polar or cationic in nature or having higher dipole moment, then that will increase the magnitude of the stabilization energy, and that will result in enhanced binding constant for this particular species. It will result in enhanced binding constant for this particular species. Now, the thing is that when you have got these non-polar groups like methyl or you have got hydrogen and tertiary butyl and R equal to H, these kind of moieties, then they are not very much soluble in water. These are essentially insoluble molecules, and if you want to actually make them soluble in water, then R is equal to SO3 minus Na plus, that is a sulfonate group has to be now introduced on the calixarene backbone. So, now you see that we are going to have a calixarene which is having SO3 minus Na plus group. And the oxygens are sitting here. You can have these OH or you can have it as R, but now you have got the sulfonated groups, and this makes the calixarene soluble. And also because it is now soluble in water, there are extensive hydrogen bonding interactions between calixarene plus water. And what has been observed is that when you have these calixarene moieties, there exists hydrogen bonding there exists hydrogen bonding, that is OH pi, between the water molecules and the pi surface of the calixarene, but these water molecules in turn are also hydrogen bonded further with this water molecule. So, you have this extensive solvation, this extensive solvation of the calixarene when you have these water molecules which are present on the rim of the sulfonate groups. So, when you have got a highly polar calixarene which is now further templated with highly polar functional groups like sulfonate, then water molecules can now extensively hydrogen bond with by OH pi, and these water molecules can further form a network with the bulk water molecules, and the sulfonate groups can also form hydrogen bonds with the water molecules. So, overall there are extensive solute-solvent interactions between the solvent as well as the calixarene, and this results in enhanced stabilization, and hence that increases the solubility of these calixarenes as well. And overall these calixarenes have many applications, and people have also looked at how we can transport metal cations across these calixarenes. For example, because people were trying to understand whether we can have mimics of crown ethers, just like crown ethers are able to transport cations efficiently, for example sodium and potassium. People also wanted to see that this compound also has got a hydrophobic interior, and it has got a hydrophilic exterior. You have got the polar functional groups, whether they can also sequester cations and transport them efficiently. And in this regard, what has been observed is for lithium, sodium and potassium, cations, the rate of cation transport across the phase boundary which is reported in moles meter square second inverse into 10 to the power 8. This particular value is being reported. That is the amount of the cation which is being transported across the phase boundary in moles per unit area per unit time is (10) for lithium ion, and it is only 2. So, when you have the Calixarenes 6, it is 10, and when you have it equal to 8, it is drops to 2. And for potassium hydroxide, the value is 13 and 10. However, for cesium hydroxide, the value dramatically improves to 810 and 996. And then if you were to increase the size further as well as the charge, for example barium, it drops to 3.2, whereas no data has been reported for n equal to 8. So, lithium is not transported efficiently, whether you have the calixarene or the calixarenes, which is larger in size. Potassium is not transported efficiently, but it is only the cesium which has got a slightly larger size and which can stabilize itself very efficiently by cation-pi interactions, that is transported because it is captured first and then it is transported and then very efficiently, and the amount of it is very high, 810 and 996 for both the calixarenes. And if you were to increase it to barium, the charge, because you increase the charge, however it does not enhance the cation transport. And people have actually looked at the structure and shown very clearly that the cesium ion stabilizes itself by cesium ion cation-pi interactions in the structure, and therefore it is very and also this is a nice steric fit. The cesium cation is slightly larger in size, and the volume it needs is also appropriate for it to fit into the cavity which is created by the calixarene. In fact, even more better for the calixarenes, and then the transport happens in a very facile way. So, this selective transport of metal cations is what has been achieved using this calixarenes. So, these are some of the important aspects of calixarenes. In the next lecture, we will now discuss about cyclodextrins. Thank you.